All right, welcome to the video that I promised. Sorry, it took me a little bit to get there, but these things happen. It's okay. So let me set my timer here first of all, so I don't go too far. Should have done that prior, but that's okay. Anyways, so last time we started our damped harmonic oscillation, so we showed that the general solution for our damped harmonic oscillator is given this way by this x value here. So this is not putting any restrictions on beta or omega zero or any of that stuff. We're again remembering that beta is equal to b over 2m, and then omega zero is equal to the square root of k over m, which is the usual natural frequency. So in this case, we discussed the underdamped situation, which is where the second term here of omega zero is greater than beta, which means this guy then is going to be imaginary. So in this case, we get a new angular frequency. So this angular frequency then is what gives us the harmonic oscillation. But our harmonic oscillation is with this new frequency, excuse me, of omega 1, which means the period then is based off of that omega 1 in this case. So perfect. So in this case, this is what gave us our, again, harmonic oscillation here, where if we look at the x versus t in this case, we had the exponential decay. So there's my exponential decay. But we still had a harmonic oscillation inside of that. So depending on my initial conditions, this guy's going to do something like this, and etc. Right? So good. So that's what we talked about last time. So good. In this case, we showed again that our amplitude is getting smaller over time. So as time increases, our amplitude is getting smaller, so that the height difference between here and here is an e to the beta tau, where again, tau here is our period. I know how to spell. There we go. So our period, and this guy here is what's known as the decrement. Good. So that's the amount at which my amplitude changes from location to location. I didn't draw it quite well here, but this decrement here is a constant, which means that it should constantly decrease by exactly the same amount. But, nobody said I had good drawing skills. So fantastic. So in the next case, we have number 2, which is when beta is exactly equal to omega 0, which means that that square root term then is going to be beta squared minus omega 0 squared is equal to simply 0. So this means that our lambda plus and minus is then simply equal to minus beta, which means we have repeated roots. Good. So in this case, since we have repeated roots, our position as a function of time then is going to be just some coefficient. Let's call that a, e to the minus beta t times, actually, let me do it this way. Let's do e to the minus beta t times some coefficient, let's call that a, plus some other coefficient b times t, because that is what we use for second order differential equations. So that's it. So basically, this is our what we call critically damped situation here. So this is critically damped. Find that guy here. Good. So this is called critically damped. So good. So first thing to note is that the exponential decrease of this guy is exactly the same as the exponential decrease of this guy here. So they both decrease as e to the minus beta t, which basically just means what? If I plotted these two on top of each other, so this is my x of t, that exponential decrease that we had is the same in both cases. So this is, again, my exponential decrease, which means for, again, my, let's see, go down a little bit further on there. But for my underdamped situation, I have the same exponential decrease as I have for then my critically damped scenario here. So the blue here is for my critically damped, and then the green here is for the underdamped situation. So they decrease exactly the same exact way, except the only difference is, again, for the green one here, this guy is critically, or in this case, exponential decay with harmonic oscillation. So it is still harmonically oscillating, but slowly. And then critically damped is basically just going directly exponentially to 0. So Difference in these guys are, kind of get it into context, this would be basically bad shocks in your car. So in this case, you would hit a bump and then basically just harmonically oscillate and bounce basically until it comes to rest. Where in the other case, this guy would be effectively good shocks, right? So good shocks. So in this case, you would just bounce, or in this case, not even bounce, but you would just exponentially go to zero. So actually, good shocks would probably be a little bit between the two. So you might have a little bit of harmonic oscillation, but it's basically just critically damped. So that's our critically damped situation. And again, energy is not conserved in this case. I'm not going to worry too much about that. And finally, case number three is when we have beta then is greater than omega zero. So in this case, we're going to have then our x of t, going back to our original expression, is basically just our original expression. So we're going to have e to the minus beta t, some coefficient, let's call that c1, e to the beta squared minus omega 0 squared, square rooted, plus C2 e to the minus beta squared minus omega 0 squared. So this is our, what we call overly damped, and let's talk about how it's overly damped, or we call just basically overdamped. So overdamped. So good. So why is this guy overdamped? Well, let's look at each one of these two terms, right? More specifically, let's look at this first term here. So basically what this means then is that my x of t goes as e to the minus beta t plus some square roots of beta squared minus omega 0 squared, which basically means that, oh, I forgot my t's here. Can't forget my t's. There we go. So basically, I have a competition then between this term here, which is then exponential decrease, so exponential decay, while I have this term here, which is trying to cause it to grow. So I have exponential growth in this case. So because of this competing different exponential terms, right? This competition between these two terms, where this one's trying to drive it to zero, right? This one wants x of t to go to zero as t goes off to infinity, where this one wants x of t to go to infinity while t goes off to infinity. So basically, what's going to happen then is if I plot this, what I'm going to get is actually still exponential decrease. However, because of that exponential growth, it's going to go to zero, but much, much, much slower, which basically means that, again, so let's plot these guys. I'm going to plot the critically in this guy here. So in this case, again, my critically damped is going to exponentially go to zero, right, this way. So this is my e to the minus beta t, where my overdamped, because it has so much damping, it actually drives an extra term inside of here, which is going to cause this guy to go to zero much, much more slowly. So in this case, this is my e to the minus beta t plus my square root of beta squared minus omega 0 squared t. Right. So again, it's still going to go to zero, but it's just not going to go to zero as rapidly, which means that, again, I basically, again, all this means is I have so much damping that that damping is basically going to lead to basically exponential growth in this case. So again, they both are going to go to zero, but this one is going to go to zero much, much, much more quickly than this one is going to be. And that's why we call it overdamped. So basically the overdamping or the damping is causing an extra growth term, which is causing this guy to go to zero much, much slower. Okay. And again, in this case, my energy then is also not conserved. So in this case, energy is not conserved. So notice a couple things here, just like critically damped, right? Here there is no harmonic oscillation, which means that's this term of beta squared minus omega 0 squared, which I'm going to call simply omega 2. This guy is not an angular frequency. Right? So this is not an angular frequency. Unlike omega 1, which was an angular frequency, because again, we have our harmonic oscillation. But in this case, because I only have exponential growth with decrease or decrease with growth, this guy is not an angular frequency. So this guy can't be an angular frequency. So these are my different cases in this case. Okay? So let's talk about this real quick. So let's talk about what we call the decay parameter. So our decay parameter. So the decay parameter is what overall shows up with that exponential term. So basically for underdamped, wow, I cannot spell today. So underdamped as well as critically damped, my exponential term here just goes as e to the minus beta t, right? So that's for both of these two terms, which means that this is true when omega 0 is greater than beta, as well as when omega 0 is equal to beta in this case. Then when I have my critically damped, or sorry, not my critically damped, but my overdamped, in this case, my decay parameter here, which we're going to call alpha, right? Or actually, no, let's call this as, so let's write this as e to the minus alpha t. So in this case, my alpha then is going to go. So in this case, alpha then is equal to beta. So this guy is going to be equal to beta minus the square root of beta squared minus omega 0 squared, which is going to be the same thing then as what? Beta minus omega 2, where again, in this case, we had beta then is greater than omega 0. So if I plot these guys, we're going to get then is what? Let's do this as alpha over omega 0. And let's plot this as beta over omega 0, just to make it dimensionless. So here, we're going to get a linear relationship between the critically damped and the overdamped. So this thing is going to increase like this until this gets to 1, where this also gets to 1, which means that in this case, again, alpha is simply equal to beta until I reach the maximum value here, which is when, in this case, omega 0 is equal to beta. In that case, I'm going to get 1. After that, this thing is then going to decrease, basically something like this, which basically means that, again, this decay parameter gets smaller as, excuse me, beta gets bigger because of basically this overdamping term in this case. So it doesn't damp as quickly. So because of that, basically this means that what the greatest amount of damping we're going to get is this point here, where this point here again is when beta is equal to omega 0. So this is the biggest amount of damping that we're going to get in this case. From here, the notes talks about some phase-based stuff, but I'm gonna kind of skip that for now. We can talk about that later if you want, or let's just move on to an example. So let's look at an example. So this example says that we have a pendulum unlength L and a bob mass of M at its end moving through oil with theta decreasing. Okay, so let's talk about that. So here's my oil. Okay. And then inside of here, I have some sort of simple pendulum. So here is my mass M. This has a length of L. And then this guy is going to be swinging basically back and forth. It's going to do something like this with some initial angle of theta. Then it says the mass bob, or in this case, my simple pendulum, undergoes small oscillations, but the oil retards the bob's motion with a resistive force. So in this case, we have our resistive force, which is equal to 2 times m times the square roots of g over L times L times theta dot. So this is my damping term. And it says that this guy is initially held at some angle. So at t is equal to 0, we have theta of 0 is equal to some theta initial. And it's held at rest, so theta dot of 0 then is equal to 0. So from here, it wants me to find the angular displacement as a function of time, my angular velocity as a function of time, and then it wants me to sketch the phase diagram in this case. So what does my phase diagram look like? So in this case, we want to plot theta versus theta dot. So this is my phase diagram for particular values of g over L, the square root of that, which is the same thing as omega 0, is then equal to 10 radians per second. And then my initial angle in this case is 10 to the minus 2 radians. So good. So let's talk about this guy. Let's see how this guy actually works. So first of all, let's use the sum of our torques in this case. So let's go back to my picture. So in this case, we know we have a gravitational force pulling downward. Right, so mg is in this direction. Good. This is a restorative, so meaning it wants to pull back into this direction. So the only torque I have in this case is my gravitational torque. So we can write out then the sum of the, well, of course, my shouldn't forget about my damping torque as well in this case. So we're going to have then, excuse me, our sum of our torques in this case, let's write it this way, is equal to I times alpha. So my torques in this case then are going to be my gravitational, which is restorative. So I'm going to get a minus mg sine of theta times the distance of L. So let's put my L in there. And then I'm going to get plus, because it's going to act in the opposite direction of my restoring torque in this case. So here, let's put an extra L on here and say it's acting at the mass itself. Right? And that's all going to equal to my moment of inertia times then my angular acceleration, which is then theta double dot. Now, since theta is small, so meaning much, much less than pi over 2, in this case, my sine of theta is going to be approximately equal then to simply theta. So let's write it this way. So good. So in this case, we're going to get a minus mgl theta plus my restoring force, which is going back to my restoring force. This guy then is going to be 2m omega 0, because again, square root of g over L is omega 0, times L squared times theta dot is then equal to, now in this case, since I have a point mass, my moment of inertia in this case is simply going to be the mass times the length squared. So I'm going to get an ml squared theta double dot. So from here, as always, what we want to do is simply isolate theta double dot. So let's do that. So in this case, we have a mass term in each term. So let's get rid of that. We have an L squared here and L squared here. So that's going to make this over an L. So in this case, we're going to get, so let's rearrange things. So I'm going to get a theta double dot minus, in this case, right? No, actually, this is in the opposite direction. Sorry, that should be a negative here. Negative. There we go. Sorry about that. So we're going to get a plus of then 2 omega 0. There we go. Theta dot. And then we're also going to get a plus omega 0 times, actually omega 0 squared times then theta is equal to 0. So in this case, notice that, what? So we have beta then is then equal to, so that factor 2 is in there. So good. So beta in this case then is going to be equal to, so this whole thing then should be, what? 2 times beta, right? So going back to our original. So this means that beta then is going to be the same thing as omega 0. And then here, we're going to get simply that when we write this out, we're going to have the square root then of omega 0 squared minus omega, or sorry, beta squared minus omega 0 squared is then equal to 0 in this case, which means that in this case, this guy is going to be critically damped. So just to remind ourselves, when we went back, we had a x double dot plus 2 times beta times x dot plus then omega 0 squared times x was equal to 0. So in this case, of course, I didn't write that down initially, but this is where that factor 2, which is the same as factor 2, comes from. So I can read off what that beta is. But anyways, so this is then my solution. So in this case, we have critically damped, which means that theta as a function of time then is going to be equal to some e to the minus beta t times then some coefficient a plus another coefficient b times t. Now from here, let's then do the time derivative of that. So theta is a function of time rate of change, then is going to be equal to, so here I'm going to take the derivative of the first, which is going to give me a negative beta e to the minus beta t times a plus b times t, plus, in this case, my original term, which is my exponential, so e to the minus beta t, times the derivative of the second, which is then just going to give me a b. Right. So good. So let's combine terms together. So in this case, I'm going to get a, what? So let's do the first term. So I'm going to get a minus a beta e to the minus beta t. And then I'm going to get a minus beta b t e to the minus beta t. And then we're going to get a plus e to the minus beta t times B. So I don't know why I just didn't pull out the E to begin with. So this is the same thing as E to the minus beta T times minus A times beta plus B times 1 minus beta T. Beautiful. So that's this guy. So good. So now let's use our initial conditions. So now what we know is at theta of 0 then is equal to theta 0. So in this case, let's plug that in. So I get theta 0 then is going to be equal to 1 times minus alpha beta, or sorry, not alpha beta, A beta, plus, in this case, then we're going to get a B equal to him. Let's see, am I forgetting anything? No, that looks about right. Okay, so cool. So from there, oh wait, I put that into the wrong expression, didn't I? I did put in the wrong expression. I should practice these things before I come on here. Anyway, so theta 0. Sorry, I was using the velocity term instead. Okay, so this is going to be just simply A. There we go. So in this case, we have A that is equal to theta 0. Good. So our another initial condition is that theta dot of 0 is equal to 0, which is then going to be equal then to 1 times minus A beta plus, in this case, this term is going to go to 0. So B, good. So in this case, I'm going to get a minus, or let's do it this way. B then is going to be equal then to A times beta, right? Good. So in this case, what we have then is this is the same thing then as theta 0 times beta. So this is my B term. So good. So let's put all that back into this expression here. So let's put these two back into both here and here. So let's go ahead and do that. So what I finally get then is that theta as a function of time is going to be theta 0 times 1 plus the square roots of g over L times t e to the minus beta times t. And then I'm going to get theta dot as a function of t then is then equal to a minus g theta 0 over L t e to the minus beta t. All right, so basically, if I now plot these guys for those particular plots I have here, or for those particular points, draw my phase space in this case. Good. So in this case, what we find then is theta dot as a function of theta, basically is going to do something like this. If I could draw that a little bit better. Good. It's going to basically do something like this. So this is my critically damped situation. So good. So let's move on. So next thing I want to talk about then is what's known as damped driven harmonic oscillators. So let's look at a driven damped or damped driven harmonic oscillator. So what is this? So this is basically, in this case, I'm going to get some extra term, which is a driving term, right? So I'm going to get, in this case, some extra force, which is my driving force, where this driving force then is basically just going to keep this guy moving. So we have some extra time-dependent force, which is basically just going to change the scenario in this case. So basically just meaning that what? It's some extra force, which is either going to cause this guy to slow down faster or increase faster or etc. So in this case, let's look at the sum of the forces. So let's say that this is some sort of driving force because it says driven in this case. So here, let's say here is my mass here in this case. So this is attached to a spring. So here's my spring. Let's say this is my equilibrium position. X is equal to 0. So we know in this case we have our spring force pushing back in this direction. We have our retarding force. Let's say it's moving to the right. So in this case, this is my velocity x dot. So I'm going to get my damping in this direction. So this is my damping force. And then let's say on top of that, we have our driving force, where our driving force then is going to be in this direction. So this is my F of t. So Newton's second law then says that the sum of my forces are then equal to my spring force plus then my damping force plus then my driving force. And these two are negative. Let's take our positive x direction to be this way. So finally, I'm going to get an mx. Let's do it this way. Mx double dot is then equal to minus k times x minus then my damping, which is going to be b times x dot. plus my f of t. Or finally, in this case, we're going to get our m. Let's see, let's define everything. I'll do that afterward. So mx double dot minus, or plus in this case, b times x dot plus k times x is then equal to f of t. So in this case, I have a what? Inhomogeneous differential equation because now I have what? This extra term. It's not equal to zero anymore. And let's go a little bit more concrete into this. Let's actually divide both sides by m. So let's rewrite this then as x double dot. And then we're going to get our plus, stop it, plus 2 times beta x dot plus omega 0 squared times x is then equal to, I'm going to call that little f of t, where little f of t then is equal to big F of t per unit mass. Okay. So good. So let's talk about this guy. So first of all, what do we have here? So what we have is some derivative, some differential operator acting onto x is then giving me my inhomogeneous part. So basically all this means then is I have some differential operator, I'm going to call that d, acting onto x, which then gives me my function f in this case. Now, looking then onto the left-hand side here, we can see then that our differential operator then is going to be then equal to the second time rate of change plus 2 times beta times my first time rate of change plus then omega 0 squared. Okay. So this is my differential operator, which then operates onto my function x and then brings it to another point of f. So basically, all this means is it's kind of like a rotation matrix, right? So basically, I have my x space here. Okay, so here's my x space. And then we're going to act on a single point here in my x space. And then our operator then is going to map that point to another point here, which is my point in my t space, basically, in this case, right? So good. So let's talk about what type of operator this is. So this is a linear operator. It's a linear operator because notice that if I have my differential operator acting onto ax, that's the same thing as a, which is simply a constant, times my differential operator acting onto that function of x. And if I have my differential operator acting onto a product of two different functions, x plus x1 plus x2, that's going to be the same thing as my differential operator acting onto the first function, plus my differential operator acting onto the second function, and etc. Okay? So this is just what? Superposition, right? So this is just superposition. So so in this case, how do we solve this particular solution? So in this case, what we do is, because this is inhomogeneous, what we have to do then is solve, first of all, the homogeneous portion. So the homogeneous portion of this, so that d of x is equal to 0, and this is our homogeneous solution. And then the other part then is now we're going to act on the particular solution now to get our particular solution so that our differential operator acting on a particular solution is what's going to then give us. So good. So let's think about this then. So that means that what? My total solution, x of t, will then be equal to our homogeneous solution plus then our particular solution. So that our differential operator acting onto total of x then is going to be our differential operator acting onto the homogeneous portion, plus then my differential operator acting onto my non-homogeneous solution, or my particular solution in this case. Again, using that superposition. This term, as we said over here, is simply 0. So this is going to be the same thing then as d acting onto my particular solution, which is the same thing as simply f. So good. So basically, all we're going to do then is break this up into our homogeneous portion and then our particular portion by looking at then our differential operator. And then basically the first term is just kind of looking for the eigenstates of our differential operator, but let's not worry too much about that at the moment. So good. So let's look at an actual concrete example of this. And my example we're going to look at is what happens if we have a sinusoidally driven harmonic oscillator. So we have a sinusoidally driven force or drive force in this case. So basically all this means then is that our f of t, little f of t, which is the force per unit mass, is going to be some coefficient f0 times, in this case, let's take this as cosine of omega t. Now, to proceed with this, it's a lot easier to work with exponentials than it is with sines and cosines. So in this case, we're going to say that, again, our Euler equation, which is e to the I omega t, is then cosine of omega t plus I sine of omega t. Which means that the real portion of e to the I omega t is the same thing as simply cosine of omega t. So what does this mean? So what this means then is what? Instead of working with x, we're going to complexify x and move that into our imaginary plane and write x as some z. Okay. So basically all I'm doing is I'm taking the real line in this case, this is my x, and then I'm going to complexify it and then move it into my imaginary plane. So this is my imaginary plane where this is my real plane. So that this portion here is going to be the real part of z, and then this portion here is going to be the imaginary part of z, right? Now, at the end of the day, the benefit of doing this, again, is it's a lot easier to solve this in terms of exponentials as opposed to solving it in terms of sines and cosines. And then when I want the actual solution of x at the end of the day, all we're going to do then is say x then is equal to the real part of z, and then we're going to undo our complexification by simply getting rid of it and doing it in this case. Okay. So good. So let's talk about this guy. So let's talk about this guy. So first of all, let's look at my particular solution. Okay. So let's assume that because our function here is going to go as e to the I omega t, because f of t then is going to be written as f0 e to the I omega t. This means my particular solution should go as some new coefficient. Let's call that c, e to the I omega t. Okay. Now, let's plug that into my differential operator. So all this means then is that my differential operator acting onto my, did I write that as an x? No, I did. Okay, good. Yes, I did. Let's go back. This should be z, particular solution, sorry. Onto z, particular solution, then is going to be equal then to, again, z particular double dot, right, plus 2 times beta times z particular dot plus omega 0 squared. Z particular then must be equal to f0 e to the I omega t. So good. So let's plug that in. So in this case, we're going to get a, what? 2 derivatives of this guy. So I'm going to get a minus. In this case, I'm going to get a minus omega 0 squared with the exponential term. I'm not going to worry about that for now. And then I'm going to get a plus with a negative sign. So it's going to become a, actually, no, I'm going to get a 2I omega. There we go. Times beta. There we go. And then I'm going to get plus, in this case, omega 0 squared, all times c e to the I omega t then is equal to f0, e to the I omega t. So in this case, my e to the I omega t's are going to cancel. So at the end of the day, let's solve this for c. So c then is going to be the same thing as f0 divided by omega 0 squared plus 2I omega beta minus omega squared. So this is my coefficient c, and notice that c here is within the complex numbers. Now, let's move this into the complex plane, basically meaning that, again, as we talked about in class before, we can take our coefficient here, and we can say that this has some sort of amplitude, or in this case, a radial direction, which is a, where in this case, a then is going to be equal to the magnitude of c, which is the square root of c times c star. And then this is going to be at some angle of delta. So that we're going to rewrite c then is equal to a e to the I delta. So this is just the polar form. So this is our polar form for a complex variable. So this is my real portion of z, and then this is my imaginary portion of z. Let's talk more about that in a second. Now, in this case, my angle of theta then, right, or sorry, of delta, will then be the what? Imaginary part of A divided then by the real parts of A. So first of all, let's go ahead and do that. So in this case, my delta then is going to be equal to the inverse tangent of my real part divided by my imaginary part. So let's see here. How do we want to do that? I'll just write it this way. So 2 beta omega divided by omega 0 squared minus omega squared. Right? A then, let's do it this way. A is going to be the square roots of C star times C or C times C star. It doesn't really matter which one. So let's multiply all that out. So this is going to be the same thing then as what? So let's write it this way. So I'm going to get a F0 squared divided then by, let's go back to our C. So it's going to be omega 0 squared plus 2 beta times I times omega minus omega squared times then the complex conjugate of that, which I already put the squared on here. So I'm going to get an omega 0 squared minus 2 beta I omega minus omega squared. Let's put a 1 there and then square root it. So the F is 0. I'm just going to pull out front. And now let's multiply terms together. So in this case, notice that what? So these two terms here are constant terms, right? So let's rewrite this then as what? Omega 0 squared minus omega squared plus 2 beta I omega. Let me put parentheses around them. That's my first term. Then my second term is going to be omega 0 squared minus omega squared, parentheses, minus then 2 beta I omega. Now, the beautiful part about doing this is what? In this case, when I multiply this out, my cross term is going to cancel. So it's going to be the same thing then as F0 times omega 0 squared minus omega, squared. Uh, in this case, I'm now going to take these portions, multiply them together. So I'm going to get a minus, but an I squared that makes it a plus. So I'm going to get a plus 4 times beta squared times omega squared. So that's this guy. So cool. So let's notice what happens in this case. So again, delta here, in this case, my delta represents the phase difference between the driving force and the resultant motion. And then notice in this case that a delay will occur between the action of the driving and the response of the system. So meaning that if we fix omega 0, right? So let's say omega 0 here is equal to some fixed number, which it mostly will be, right? Because that's just some sort of constant. So this guy is a fixed number. And then the phase in this case is going to increase from omega is equal to 0, so that delta is equal to 0, right? So if omega is equal to 0, I have the arctangent of 0, which is 0. And then it's going to approach pi over 2 when omega 0 is equal to 0. So in this case, as omega goes to omega 0, in this case, our delta then is going to become the arctangent of some constant, in this case, divided by 0, which is the same thing as the inverse tangent of infinity, which is equal to simply pi over 2. Okay? Now, in this case, when omega goes to infinity, in this case, delta then is going to become simply equal to what? So in this case, we're going to get minus 2 beta. Let me do it this way. Arctangent. So this guy's going to become what? So I'm going to get a 2 beta omega divided by an omega 0 squared, right? Because that omega 0 is not going to matter. So in this case, this term's going to cancel this term, which means this term then is going to go to simply pi. So basically, all this means then is if we plotted delta versus omega, this thing is going to start up at 0, and then it's going to shift to, let's see here, this guy's going to become what? As omega 0 goes to him. So at omega 0 in this case, so this is omega 0, this guy's going to increase then to pi over 2. And then it's going to, what? Increase some more and then basically go to pi at some other stage. Now, let's talk about what else happens. So let's go back to the Z particular. So we said this guy then is going to be equal to C e to the I omega t. But we also rewrote this then as A e to the I omega t minus delta, right? Times I. Because in this case, again, we're saying C then is equal to some A e to the I delta. Now let's plug this then into our actual solution. So our actual solution then is going to be some x of t then is equal to some coefficient C1 e to the lambda plus t, and then plus some C2 e to the lambda minus t, where these guys are going to be damping terms. Now, in this case, the damping terms doesn't really matter, but all we care about in this case is that E then goes as minus beta t, right? So these two terms go just simply that way. And then whether it is what, critically damped, underdamped, or overdamped, they all go basically exactly the same way, right? And then we're going to get this plus. In this case, we're going to take the real part of that, which is going to give me an A cosine of omega t minus delta. Now, in all these cases, it doesn't really matter what kind I have, whether it's critically damped, underdamped, or overdamped. These terms here, as t goes off to infinity, this term is going to go to zero, which means that as t goes to infinity, x of t then is going to become equal to simply a cosine of omega t. Now, what's interesting about this is it doesn't matter if it is overdamped, underdamped, or critically damped, all solutions are going to go to this term here. So this is what's known as, or at least these terms here are what are known as transients, which means that they are important for early times. So these are important for early times, or early times. But for late times, they don't matter. So this term here is what we call the attractor. So all of these terms will all condense or all uh, converge onto this particular solution here as t goes off then to infinity. So let's talk a little bit more about this because this actually has some other interesting effects on it. So let's go a little bit further. So let's look at what's known as resonance. Let me see how much time I have left. Okay, I only got a little more time. So let's look at what's called as resonance. Now, we're mostly going to be interested in is what happens to that C term. So what happens to our C here? So first things first, notice that if I took the derivative of C with respect to omega, and then we're going to set this equal to, or evaluate it at some term, which was what we're going to call the resonance frequency. Which means that this guy is going to be equal to zero. So this is our maximum value, or the biggest at which C can be, or the smallest, depending which way that works. But this guy is going to be equal to, I'll spare you the details of this derivative. This is going to become f0 squared times 4 omega resonance times omega resonance squared minus the natural frequency squared plus 8 beta squared omega resonance. Then all divided by omega resonance minus the natural frequency squared plus 4 times beta squared omega resonance squared on the whole entire bottom here squared. Now, what we're looking for is simply what is omega resonance to make this true? Well, if I go through all the algebra, what I finally find is that omega resonance is equal to plus or minus the square root of omega 0 squared minus 2 times beta squared. Okay. So basically, what does this say? So this says as beta increases, the resonance frequency is lowered and no resonance occurs when this thing would become imaginary, right? Which basically means that what? When beta becomes then equal to or greater than, in this case, omega 0 divided by the square root of 2, in this case, we're going to have no resonance, right? So no resonance in this case. Resonance. So basically, let's go look at this a little bit further. So let's define this new quantity. Let's call this a Q factor. So let's define then a Q factor. where our Q factor then we're going to define as Q, which is then omega resonance then divided by twice of beta. Now let's look at what actually happens then for C in this case. So let's plot C versus omega. Okay. So in this case, we get C divided by the F0. So just make this guy dimensionless. And notice what happens in this case. So basically what happens then is what? As, in this case, omega approaches omega resonance. So this is my resonance frequency. Basically what happens is this guy starts off, again, in the fact of, in this case, let's go back to C. Where was my C? Let's go back to C. There's my A, so let's go to C. So there's C. So as omega, or as omega, in this case, goes to omega 0, we're going to get basically a, well, say omega resonance. What happens in this case then is we're going to get this nice, beautiful spike, right? So let's go back. So basically what happens then is this thing's going to be mostly flat, start to increase until I get to omega is equal to omega r, and then this thing is going to come back down, which basically means that this amplitude here is going to become very large, right? So C in this case, again, is equal to my amplitude, which means my amplitude then is going to blow up. So C then is going to go off or get bigger, in this case, become its maximum at omega is equal to omega r, right? So basically, once then the driving frequency matches what's known as this resonance frequency, then this thing is going to basically blow up to be huge. So this is when the amplitude of oscillation is going to become equal to a maximum amount of value. Now, when that happens, then, as we talked about way back when in Physics 206, this thing then is going to simply become what? A maximum amount of energy because we have our maximum amount of harmonic oscillation because our amplitude now becomes the maximum. And this is what's going to cause a building to fall down, right? It's going to cause a bridge to collapse like the Tacoma Bridge because our external driving frequency is going to match the natural resonance frequency of the system, basically causing it to break down. Now, the Q factor can be completely destroyed if there is too much, right? So the damping may be completely destroyed if the damping is too large and the Q value is basically very, very small. So if I increase the damping factor too much, as we saw with the overdamped, in this case, it can actually destroy the exponential decrease, causing this thing then to overall decrease. Now, this Q factor basically means that what? The smaller the Q factor is, the smaller this increase here is going to be, right? So basically meaning that if I had a small Q factor, we're going to get a small amplitude. So this is going to be a small Q factor. And as my Q factor increases, then we're going to get a bigger and bigger, in this case, resonance frequency until eventually, when this Q factor is going to go off to infinity, this thing is basically going to blow up and then become an infinite spike, which means it's going to become basically like a delta function. So in this case, as Q goes off to infinity, the size of this is going to go off to infinity. So this is our Q factor. But again, point of this is, again, resonance. So as my external frequency goes to the resonance frequency, the amount of amplitude, or in this case, the amount of harmonic oscillation is going to become bigger and bigger and bigger and bigger and bigger until eventually it's going to become so large with this Q factor here that it's just going to cause the system to basically fall apart in this case. So that's pretty much it. Pretty much out of time. So last thing we'll talk about tomorrow then is Fourier analysis. We're going to look at periodic systems and talk about how things change with periodic systems. And then that'll pretty much be the end of this chapter. So we can start moving into things like variational principles and Lagrangian mechanics. So that's pretty much it. Hopefully all that made sense. I know it didn't always make sense, but that's okay. All right. Let me know if you have any questions in class, and I'll talk to everybody later. Bye.